Science fiction has long fascinated audiences with the idea of extraterrestrial contact. But could these imaginative tales one day become a reality? There's a reason Hollywood is so captivated by the concept of first contact with aliens. It would represent the most groundbreaking scientific discovery in human history, raising fundamental questions about our place in the universe. Alternatively, we might find that we are indeed alone in the cosmos, a possibility that is equally profound and humbling. 45 years ago, the Abrams Observatory embarked on an unprecedented mission by sending a radio message deep into the vastness of space. This transmission marked humanity's first deliberate attempt to communicate with a hypothetical intelligent civilization beyond our galaxy. The message, now journeying through the cosmos, is currently about 1,000 miles away from its point of origin. It is headed towards a distant star cluster, known as the M13 globular cluster, which lies approximately 25,000 light-years from Earth. This message contains detailed information about our planet, including our location within the Milky Way and the composition of our DNA. The intent behind this interstellar communication was simple: to say hello to any potential extraterrestrial listeners. Yet, this gesture also sparks a profound question. Are we truly alone in the universe? The likelihood of intelligent alien civilizations existing somewhere in the vast expanse of space is a topic of intense debate and curiosity. The universe is staggeringly large, filled with countless stars and planets. If life emerged relatively early on Earth, as it appears to have done, why hasn't it manifested elsewhere? And if life does exist beyond our planet, how many extraterrestrial civilizations might we eventually encounter? To explore these questions, astronomer Frank Drake developed what is now known as the Drake equation. This mathematical formula applies logical reasoning to estimate the probability of life existing beyond Earth. According to the Drake equation, there could be at least 100,000 intelligent civilizations in the Milky Way galaxy alone. In recent decades, the discovery of exoplanets, planets that orbit stars outside our solar system, has added a new dimension to this calculation. To date, scientists have identified approximately 4,000 exoplanets, and new discoveries are being made regularly. However, astronomers believe that these discoveries represent only a small fraction of the planets that actually exist in the universe. If the universe is so adept at creating planets, perhaps it is equally capable of creating the conditions necessary for life. When Drake first proposed his equation, the existence of exoplanets was still unconfirmed. But now, the scientific consensus is that planets are more numerous than stars. Despite the apparent rarity of life, the sheer number of opportunities for it to arise in the universe means that it could be more widespread than we might think. The universe likely teems with a diverse array of life forms, possibly including many complex alien civilizations. This is not the stuff of science fiction, it is a matter of basic probability. Yet, if the universe is so vast and filled with potential for life, why haven't we detected any other civilizations? One potential answer lies in the geography of our own galaxy. Earth is located in a relatively quiet suburban region of the Milky Way. The galaxy spans about 100,000 light-years across, meaning that even if there were millions of civilizations scattered throughout, the vast distances between stars could make communication nearly impossible. For example, a radio signal sent from one side of the Milky Way to the other would take 75,000 years to reach its destination, assuming it travels at the speed of light, the ultimate speed limit in the universe. The immense scale of the galaxy presents a formidable obstacle to any form of contact. The message sent from the Abrams Observatory 45 years ago is still en route to its intended destination, travelling at an impressive speed of 1,000 kilometers per hour. However, it remains far from its target, underscoring the challenges of interstellar communication. The laws of physics, particularly the speed of light, act as a barrier, preventing signals from crossing such enormous distances in a reasonable time frame. Even if intelligent civilizations exist within our galaxy, they may be too distant for us to ever establish contact. But despite these challenges, humanity remains undeterred. Efforts to detect extraterrestrial life continue with the aid of advanced technology. The Breakthrough Listen project is a leading initiative in this quest. This global effort employs cutting-edge technology, including radio and optical telescopes, to scan the heavens for any signs of communication from alien civilizations. Breakthrough Listen operates like a cosmic eavesdropper, listening intently to the universe in the hopes of catching an interstellar conversation. At present, the project is focused on monitoring the 1,700 stars closest to Earth, hoping to detect something extraordinary. However, the search has so far been met with silence, much like waiting for a phone call that never comes. The absence of evidence, however, does not equate to evidence of absence. The Breakthrough Listen project is still in its early stages, and there is much more of the universe left to explore. The challenge is akin to finding a needle in a cosmic haystack, requiring immense patience and persistence. Given that our galaxy contains roughly 250 billion stars, searching for a specific signal is like trying to find a single room in a city with 250 billion buildings. It is a colossal task, one that demands determination and unwavering commitment. Given the vastness of the universe, it is possible that we may need to exercise patience before receiving any definitive signs of alien life. Although we are eager to capture signals from extraterrestrial civilizations, the enormous distances involved mean that any communication we do intercept may be outdated by the time it reaches us. Even if we were to receive a message from a distant civilization, the sender might have long since disappeared, their message becoming nothing more than a historical echo. In the grand dance of the cosmos, humanity might be arriving late to the party. Perhaps alien civilizations have already come and gone, leaving no trace of their existence. Earth, with its rich history spanning approximately 4.5 billion years, has only recently given rise to intelligent life. From the perspective of the universe, humanity is still in its infancy, having only developed advanced technology in the last few centuries. Yet, the universe is home to star systems far older than our own. We often refer to ourselves as a spacefaring civilization, boasting the ability to launch rockets and communicate via radio waves. But what if we were to encounter a civilization with millions of years of technological advancement ahead of us? The Kardashev scale offers a framework for measuring the progress of civilizations based on their energy consumption. This scale divides civilizations into 3 levels. Type 1. Civilizations can harness all the energy available on their home planet. Type 2 civilizations can tap into the energy of their entire solar system. And Type 3 civilizations are true giants, capable of utilizing the energy of their entire galaxy. Unfortunately, humanity has not yet reached even the first level on this scale. Our civilization is currently rated at a modest 0.7, as we have not fully mastered the resources available on Earth. Despite our relatively low standing on the Kardashev scale, we are striving to catch up with our potentially more advanced neighbours in the universe. One can only imagine the remarkable feats a civilization could achieve once it reaches the 2nd or 3rd level. For instance, a Type 2 civilization might construct massive solar panels, known as Dyson spheres, to encase entire stars and harness their energy. The concept of the Dyson sphere, first proposed by physicist Freeman Dyson, envisions a colossal structure that could capture nearly all of a star's light, allowing only a small amount of infrared radiation to escape. As these spheres absorb sunlight, they would warm up and emit thermal infrared signals that could potentially be detected by our instruments. In 2015, NASA's Wide Field Infrared Survey Explorer, WISE, conducted a search of 100,000 nearby galaxies for signs of these advanced civilizations. The goal was to identify the telltale infrared signals that a Dyson sphere might produce. Unfortunately, this extensive survey did not yield any conclusive evidence of such civilizations. Given the age of the universe, other civilizations should have had ample time to evolve and develop sophisticated technologies. So where are they? It's possible that these advanced civilizations have existed and faded away in the long history of the cosmos. When we consider the relatively short span of human civilization, around 300,000 years, it becomes clear that our time on Earth is but a fleeting moment in the grand timeline of the universe. Venus, one of Earth's closest neighbours in the solar system, offers an intriguing comparison. Similar in size and mass to Earth, Venus shares many of our planet's characteristics, including a central iron core, a rocky mantle, and a thin crust. However, Venus's core and internal structure remain less understood than Earth's. Unlike Earth, Venus rotates in the opposite direction, a unique trait among the planets of our solar system. Scientists are still trying to understand the cause of this phenomenon, with some speculating that a past collision with a massive object may have altered Venus's rotation. Venus also rotates extremely slowly, taking 243 Earth days to complete one rotation, making it one of the slowest spinning planets in the solar system. This sluggish rotation contributes to the lack of a significant magnetic field on Venus, which in turn has profound implications for the planet's atmosphere and potential to support life. Another curious fact about Venus is that its day is longer than its year. A single day on Venus, defined by one complete rotation on its axis, lasts approximately 116.75 Earth days. In contrast, it takes about 225 Earth days for Venus to orbit the Sun. This means that on Venus, a day is nearly twice as long as a year, a rare and intriguing characteristic among the planets in our solar system. Despite these differences, Venus shares some similarities with Earth, such as its surface gravity, which is about 90% of that on Earth. This means that if you were to stand on Venus, you would feel slightly lighter than you do on Earth. However, the extreme atmospheric pressure and scorching temperatures on Venus would make it impossible for humans to survive without specialized protection. The planet's surface, shaped by volcanic activity and other geological processes, appears relatively young when viewed from a geological perspective. The stark contrast between Earth and Venus highlight the diversity of planetary environments within our solar system and beyond. As we continue to explore the cosmos, we may find that life, if it exists elsewhere, could be vastly different from anything we have imagined. The search for extraterrestrial civilizations is a monumental task, one that requires not only advanced technology, but also a deep sense of curiosity and determination. As we listen for signals from the stars, we remain hopeful that one day we will discover that we are not alone in the universe. Until then, the quest for knowledge continues, driving us to explore the unknown and expand our understanding of the cosmos. Venus is an intriguing celestial body within our solar system, holding a unique position as Earth's so-called twin due to its similar size and composition. However, the similarities end there, as Venus's environment is hostile and markedly different from Earth's. The planet's surface is relatively young in a geological sense, estimated to be between 300 to 600 million years old. Scientists hypothesize that Venus has undergone a cyclical process in which internal planetary heat has periodically resurfaced the entire planet. This process, likely driven by volcanic activity, has smoothed out the surface in global events, leaving Venus with fewer impact craters than would otherwise be expected. The evidence of extensive volcanic activity on Venus is overwhelming. The planet is dotted with thousands of volcanoes, ranging in size from small ones about 2 kilometers in diameter to massive ones exceeding 240 kilometers across. This immense number of volcanoes surpasses that of any other planet in the solar system. Interestingly, Venus lacks the significant tectonic activity that characterizes Earth, such as the large-scale plate movements that shape our planet's surface. However, it does have mountain ranges and rift valleys similar to those found on Earth. The tectonic features of Venus are different from Earth's in that the planet does not have distinct tectonic plates. This absence is possibly due to Venus's slow rotation, which might limit the Coriolis effect needed to drive large-scale tectonic processes. Despite the absence of tectonic plates, Venus does exhibit tectonic activity, albeit on a smaller and less defined scale than Earth. One of Venus's most striking features is its atmosphere, which is composed predominantly of carbon dioxide, making up 96.5% of the atmosphere. Nitrogen constitutes the majority of the remaining 3.5%, with trace amounts of other gases such as sulfur dioxide, water vapour, carbon monoxide, and helium. This composition is vastly different from Earth's atmosphere, which is dominated by nitrogen and oxygen. The thick, toxic atmosphere of Venus is uninhabitable for humans and most known life forms. The atmosphere of Venus is organised into several layers, including the troposphere, which extends from the surface to about 60 kilometres in altitude, the mesosphere, reaching up to about 90 kilometres, and the thermosphere, which extends further upward. Above 200 kilometres from the surface, there is a transition region called the exosphere, where the atmosphere merges into space. The high concentration of carbon dioxide in Venus's atmosphere creates an intense greenhouse effect, trapping heat and making Venus the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases absorb solar radiation and prevent it from escaping back into space, leading to surface temperatures averaging around 467 degrees Celsius, 872 degrees Fahrenheit, hot enough to melt lead. Despite being relatively rare, clouds on Venus are composed primarily of sulfuric acid. These thick clouds effectively scatter and reflect sunlight, allowing only a fraction of it to reach the surface. As a result, the temperature on Venus is nearly uniform across the planet, with minimal variation between day and night or between the equator and the poles. This uniformity creates a furnace-like environment that is almost constant across the entire surface. The atmospheric pressure on Venus is also extraordinarily high, about 92 times that of Earth's sea level, equivalent to the pressure found about 900 metres, 3,000 feet, underwater on Earth. However, in the Venusian atmosphere, approximately 50 kilometres above the surface, the pressure and temperature conditions are similar to those found on Earth, making this layer of the atmosphere the most Earth-like environment on the planet, despite the toxic air. Venus's surface is perpetually shrouded by thick, opaque clouds that obscure its surface from view. These clouds cover the entire planet and reflect about 75% of the sunlight that reaches Venus back into space, making the planet shine brightly and be easily visible from Earth. The upper atmosphere of Venus is characterized by incredibly strong winds, which can reach speeds of up to 700 kilometers per hour, 430 miles per hour, much faster than the strongest hurricanes on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface below. Venus boasts the highest mountains in the solar system, with peaks rising about 20 kilometers, 12 miles, above the planet's average surface level. The planet's surface is also dotted with numerous impact craters, extensive lava flows, and unique surface features such as coronae, circular structures formed by upwelling of hot material. These structures, influenced by Venus's slow rotation and thick atmosphere, exhibit complex fracture patterns. Although Venus does not experience significant seismic activity like Earth, recent studies suggest that the planet may still be geologically active, indicating ongoing internal processes that could reshape its surface over time. Since the dawn of space exploration, Venus has been a prime target for scientific study. Missions from the Soviet Union, such as the Venera and Vega programs, the United States Pioneer Venus project, and the European Space Agency's Venus Express mission have significantly expanded our understanding of Venus. These missions achieved many firsts, including the first human-made objects to enter another planet's atmosphere and successfully land on its surface, providing invaluable data about Venus's atmosphere and surface conditions. More recently, NASA's Magellan orbiter used radar to penetrate Venus's thick clouds and map nearly the entire surface, revealing the planet's geological features in detail. Despite the challenges posed by Venus's extreme environment, scientists remain deeply interested in its surface features and geological history, continuing to plan future missions to explore the planet further. NASA's planned missions, Veritas and Da Vinci Plus, aim to study Venus's geological history and atmospheric conditions in greater detail to determine if the planet ever had liquid water. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth evolved so differently, despite their similar sizes and compositions. Additionally, Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns, providing ongoing insights into this enigmatic planet. Venus is a fascinating and challenging world, and while its environment is inhospitable, its similarities in size and composition to Earth, along with signs of past potential water and geological activity, make it a subject of great scientific interest. As we prepare for new missions to Venus, we stand on the brink of significant discoveries that could reshape our understanding of Venus, the solar system, and our place within it. Venus is both a cautionary tale and an opportunity for scientific discovery, offering a glimpse into the possible fates of planets and the diverse conditions that can exist within our solar system. Jupiter, the giant of the solar system. Jupiter, the largest planet in our solar system, has long captured the imagination of astronomers and space enthusiasts alike. With its vibrant stripes and iconic Great Red Spot, Jupiter is instantly recognizable, but its significance extends far beyond its size and famous storms. As space technology and exploration have advanced, our knowledge of Jupiter has grown exponentially. Jupiter is primarily composed of hydrogen and helium, and its diameter is about 11 times that of Earth, making it large enough to contain over 1,300 Earths. Despite its enormous size, Jupiter has the shortest day of all the planets, rotating once every 9.9 hours. Jupiter's magnetic field is the strongest in the solar system, generated by the rapid rotation and movement of metallic hydrogen within its outer core. Jupiter's famous stripes, or bands, are actually zones of high-pressure regions characterized by lighter-colored clouds, while the darker regions are low-pressure zones. The vivid colors we see are caused by different types of clouds. Ammonia crystals create white bands, while other chemical compounds produce red, brown, and yellow hues. The Great Red Spot, one of Jupiter's most recognizable features, is a massive, persistent high-pressure area in the atmosphere that has been raging for at least 300 years, making it one of Jupiter's most enduring and prominent characteristics. The Great Red Spot is located in Jupiter's southern hemisphere and is encircled by fast-moving jet streams that move westward, known as the South Equatorial Belt. The exact cause of the spot's reddish colour remains a subject of research. Some theories suggest it could be due to complex organic molecules, red phosphorus, or sulfur compounds. The chemical reactions responsible for the spot's vivid coloration are still not fully understood. The storm rotates counterclockwise, completing a rotation approximately every 6 days. Interestingly, the size and colour of the Great Red Spot can change, reflecting the complex interactions between the storm and its surrounding environment. Unlike storms on Earth, which typically last only a few days or weeks, the Great Red Spot has persisted for centuries. This longevity may be due to Jupiter's rapid rotation and the lack of a solid surface, which minimises friction and energy dissipation, allowing the storm to endure. Studying the Great Red Spot provides a window into understanding Jupiter's atmospheric dynamics. As a gas giant, Jupiter's conditions are vastly different from those on Earth, and unravelling the mysteries of this swirling vortex not only sheds light on Jupiter, but also helps us understand broader principles of atmospheric behaviour in planetary systems. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each moon is a world unto itself. Io is the most volcanically active body in the solar system, with a surface covered in sulfur and sulfur dioxide, giving it a colourful appearance. Europa has a thick ice shell, beneath which scientists believe there could be a subsurface ocean, making it a potential candidate for harbouring extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto is characterised by its heavily cratered surface, and there is evidence that it may also have a subsurface ocean. Jupiter has at least 79 moons, and there could be even more that have yet to be discovered. Many of these moons are small and irregularly shaped, likely captured by Jupiter's strong gravitational pull. The diversity of these moons and their interactions with Jupiter provide a rich field of study for scientists. The ongoing exploration of Jupiter and its moons by spacecraft like NASA's Juno mission continues to reveal new insights into these fascinating worlds. Jupiter's ring system, discovered in 1979 by the Voyager 1 spacecraft, is faint and composed primarily of dust particles that are likely generated by meteoroid impacts on its smaller moons. Unlike the bright, icy rings of Saturn, Jupiter's rings are dark and difficult to observe from Earth. The rings are divided into 3 main components: the halo, the main ring, and the gossamer rings. The halo is the innermost part, while the gossamer rings extend the farthest from the planet. Jupiter's immense magnetic field is another of its standout features, extending millions of kilometres into space and far beyond the orbits of its moons. This magnetic field traps particles from the solar wind and generates powerful radiation belts, creating an environment that would be extremely hazardous to humans. Jupiter's magnetosphere, the region around the planet dominated by its magnetic field, is the largest structure in the solar system. The planet's magnetic field is thought to be generated by the movement of metallic hydrogen deep within its interior. Unlike Earth's iron core, which generates our planet's magnetic field, Jupiter's magnetic field is produced by the motion of hydrogen under extreme pressures, where it behaves like a metal. This magnetic dynamo is responsible for the intense radiation belts surrounding the planet. Jupiter's atmosphere is divided into several layers, with the visible clouds being just the outermost layer. Beneath these clouds lies a thick layer of hydrogen and helium gas, which transitions into a layer of metallic hydrogen due to the immense pressure. Below the metallic hydrogen layer, scientists believe there may be a core composed of heavier elements, but its exact composition remains uncertain. Jupiter's internal heat, left over from its formation, drives powerful atmospheric dynamics. This heat causes convection currents that contribute to the planet's complex weather patterns, including the formation of its famous belts and zones. Unlike Earth, where weather is driven primarily by solar energy, Jupiter's weather is largely influenced by its internal heat. This internal heat also helps power the planet's storm systems, including the Great Red Spot. In addition to its internal heat, Jupiter is bombarded by intense radiation from the Sun and cosmic rays from space. This radiation interacts with the planet's atmosphere, leading to the formation of auroras around its poles. These auroras are similar to those seen on Earth, but are much more intense, covering a larger area and emitting higher levels of energy. The auroras on Jupiter are caused by the interaction of charged particles from the solar wind with the planet's magnetic field. These particles are funneled along magnetic field lines toward the poles, where they collide with atoms and molecules in the atmosphere, creating the glowing light shows. Unlike Earth's auroras, which are primarily green and red due to oxygen and nitrogen, Jupiter's auroras are primarily in the ultraviolet spectrum and are invisible to the naked eye. The exploration of Jupiter has been a major focus of planetary science for decades. The Pioneer and Voyager missions provided our first close-up views of the planet and its moons. Galileo, the first spacecraft to orbit Jupiter, made numerous discoveries, including the observation of volcanic activity on Io and the evidence of subsurface oceans on Europa. Currently, NASA's Juno mission is providing detailed data on Jupiter's atmosphere, magnetic field, and interior structure. By studying Jupiter, we not only learn about this giant planet, but also gain insights into the formation and evolution of the solar system as a whole. Jupiter's massive size and strong gravitational influence have played a significant role in shaping the orbits of other planets and in protecting the inner solar system from comet impacts. Understanding Jupiter helps us understand the processes that govern our solar system and potentially other planetary systems throughout the galaxy. The many satellites and faint ring systems that surround planets like Jupiter make them captivating subjects for continued telescope observations and space exploration missions. Unlocking the secrets they harbour could significantly enhance our understanding of the universe. The existence of Jupiter and its complex system highlights the diverse and expansive nature of our solar system. It also raises the possibility that microbial life might exist on other celestial bodies within our solar system, like Mars, or that intelligent civilizations might reside on planets orbiting other stars. These are among the intriguing questions explored by the Fermi paradox. The Fermi paradox grapples with the apparent contradiction between the high probability of intelligent life existing elsewhere in the universe and the lack of evidence for or contact with such civilizations. The paradox considers the vast number of stars in the Milky Way galaxy, many of which likely have planets that could support life. If there are potentially millions of intelligent civilizations just in our galaxy, why haven't we encountered them? Some people believe that we have already had encounters with extraterrestrial civilizations, as evidenced by countless stories of alien sightings and abductions. However, these claims are often supported by little concrete evidence. When speculating about what extraterrestrial beings might look like, popular culture often imagines them as green, large-eyed creatures. But in reality, it's highly unlikely that aliens would resemble this image. Predicting their appearance is almost impossible, as it would depend entirely on the conditions of the planet where they evolved. For instance, if an alien species evolved on a planet with high gravity, their physical form would likely be adapted to that environment, possibly resulting in beings that look nothing like humans. Why would aliens visit Earth? There are several possible reasons. Some scientists suggest that extraterrestrials might be interested in our planet due to its unique conditions and the way life has managed to survive here. Another reason for their visit could be an attempt to make contact with us. If there are indeed millions of intelligent civilizations in the galaxy, it's conceivable that some might try to communicate with us. However, if they do, their methods of communication might be so different from ours that we would find it challenging to understand them. If we were ever to encounter extraterrestrials, many scientists believe that we should approach any interactions with caution. Avoiding sudden movements or actions would be wise, as these could be misinterpreted by aliens. Instead, if contact were to be made, it should be done in a peaceful and non-threatening manner. This brings us back to the Fermi paradox. If there are so many intelligent civilizations, why haven't we seen any evidence of them? One possibility is that advanced civilizations tend to self-destruct as their technology progresses. Whether through environmental degradation, warfare, or other catastrophic events, many intelligent civilizations might reach a point where they can no longer sustain themselves, ultimately leading to their downfall. As a result, their signals become undetectable. leaving us with no evidence of their existence. Whatever the reasons behind the Fermi paradox, it remains a mystery and a topic of much speculation. Now, let's consider the possibility of life existing within our own solar system. While we have yet to find evidence of intelligent life, there are some promising signs. For example, there is evidence of subsurface oceans on some of Jupiter's moons, which could potentially support life. Discovering microbial life within our solar system would be a monumental find and would have profound implications for our understanding of life in the universe. Contact with an extraterrestrial civilization could have a significant impact on our society. Our understanding of the universe might challenge our existing beliefs and worldview. We might need to reassess our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. Such contact could also raise ethical questions about how intelligent species should interact with others and the responsibilities that come with such interactions. Another potential impact of contact with extraterrestrials could be on our technological and scientific advancement. If we were to encounter a more advanced civilization, we might learn from their technology and knowledge, accelerating our own progress. On the other hand, if the aliens are hostile, they could pose a threat to us. It's difficult to determine whether extraterrestrials would be a danger to us, given the lack of concrete evidence of their existence and intentions. Some people believe that if aliens are technologically superior and capable of conquering or destroying us, they could be very dangerous. Others argue that any civilization advanced enough to travel through space might have a more complex understanding of the universe and might be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, merely observing us from a distance without any intention of interacting with us. We cannot draw any definitive conclusions about their intentions or behaviour. However, many scientists believe that the search for extraterrestrial life should be conducted with an open mind and healthy curiosity, rather than fear or paranoia. Regardless of the potential impact of discovering intelligent life, we will continue to develop new technologies to improve our ability to detect signals and evidence of other civilizations. While the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthwhile endeavour in itself. There are some hypotheses based on the Fermi paradox that suggest advanced extraterrestrial civilizations may have existed for a long time, but have been eliminated by certain natural filters. If these extraterrestrial beings do exist, it raises the question of whether their forms and environments would resemble those on Earth. This idea stems from a theory that certain filtering conditions, whether astrophysical, physical, biological, or social, act as constraints on the emergence and development of advanced civilizations. Possible filters could include catastrophic events, astrophysical phenomena, or self-destructive behaviours inherent in intelligent societies. If extraterrestrial life does exist, it is possible that their forms and environments would not be similar to those on Earth. Life could evolve in different ways depending on the unique conditions of each planet. The diversity of planetary environments and the adaptability of life mean that alien organisms might have different biochemistries and physical characteristics. Rocky planets like Earth are considered ideal for supporting life due to their specific conditions, but they are also quite vulnerable to various threats. One significant threat comes from intense stellar events, such as gamma-ray bursts. These bursts are so powerful that they can obliterate planets in distant parts of the universe and might even affect entire galaxies. Imagine a massive star exploding in our galaxy, releasing a lethal energy shockwave directed at our planet. Gamma-ray bursts are the most powerful explosions since the Big Bang, striking without warning and releasing radiation that could heat the upper atmosphere, causing our ozone layer, and even the entire atmosphere, to heat up. Humans would perish from radiation exposure, and as the ozone layer erodes, lethal doses of radiation would spread worldwide. Rising temperatures would trigger storms, tsunamis, and hurricanes, ravaging land and sea. most life forms would be destroyed. This may sound like science fiction, but if a gamma-ray burst were to strike Earth, it would be a catastrophic event. Even if some intelligent species managed to survive these natural events, the situation would still be devastating. One significant threat comes from intense stellar events, such as gamma-ray bursts. These bursts are so powerful that they can obliterate planets in distant parts of the universe and might even affect entire galaxies. Imagine a massive star exploding in our galaxy, releasing a lethal energy shockwave directed at our planet. Gamma-ray bursts are the most powerful explosion since the Big Bang, striking without warning and releasing radiation that could heat the upper atmosphere, causing our ozone layer and even the entire atmosphere to heat up. Humans would perish from radiation exposure, and as the ozone layer erodes, lethal doses of radiation would spread worldwide. Rising temperatures would trigger storms, tsunamis and hurricanes, ravaging land and sea. Most life forms would be destroyed. This may sound like science fiction, but if a gamma-ray burst were to strike Earth, it would be a catastrophic event. Even if some intelligent species managed to survive these natural events, the situation would still be devastating. Additionally, there is another risk: self-destruction. This risk stems from our own experiences on Earth. Technological advancements have given us the ability to alter the climate and develop nuclear weapons. The brief lifespan of advanced civilizations could explain why there are so few observable civilizations. Many civilizations might have emerged, but their existence was short-lived due to self-inflicted destruction. The scarcity of long-lasting civilizations could explain why there are limited opportunities for interaction with extraterrestrial beings. If we find a civilization that has self-destructed due to pollution or conflict, it would emphasize the importance of avoiding similar pitfalls in our quest to understand the universe. We can only hope that some advanced alien species have successfully navigated these potentially deadly cosmic filters. If we are fortunate, we might catch a glimpse of a civilization that has managed to survive and thrive for an extended period. In the future, it is possible that an extraterrestrial civilization may visit us. Although we tend to imagine aliens as being similar to us, the reality may be quite different. Our understanding of life on Earth shapes our imagination, leading us to assume that they live on planets similar to ours. However, most life in the universe might not adhere to the rules of life and planetary conditions that we are familiar with. The search for extraterrestrial life and the Fermi paradox present us with profound questions about our place in the cosmos and the nature of life beyond Earth. As we continue to explore and seek answers, we must remain open to the possibility that the universe holds many more mysteries than we can currently imagine. The multitude of moons and the delicate ring systems that orbit planets such as Jupiter render them exceptionally intriguing subjects for ongoing astronomical observation and space missions. These celestial features captivate our interest and provide us with invaluable opportunities to delve deeper into the mysteries of our universe. If we could decipher the secrets embedded within these distant worlds, it would significantly enhance our comprehension of the cosmos. Jupiter's existence alone underscores the intricate and diverse nature of our solar system, revealing its vast and multifaceted character. This complex nature suggests that life may exist in other corners of our solar system, such as on Mars, or that intelligent civilizations could inhabit planets orbiting other stars. Such possibilities are at the heart of the Fermi paradox, a profound scientific conundrum. The Fermi paradox addresses the puzzling discrepancy between the high probability of extraterrestrial life and the lack of concrete evidence or contact with such civilizations. The paradox arises from the sheer number of stars within our Milky Way galaxy, many of which are likely to have planets capable of supporting life. With potentially millions of intelligent civilizations existing just within our galaxy, why have we not encountered any signs of their existence? Some individuals speculate that we may have already had encounters with extraterrestrial beings, as evidenced by numerous reports of UFO sightings and alien abductions. However, these accounts often lack substantial evidence to support their claims. When it comes to visualizing extraterrestrial life, popular culture frequently depicts aliens as green beings with large eyes. This stereotypical image, however, is unlikely to be accurate. Predicting the appearance of extraterrestrial life forms is inherently speculative, as their physical characteristics would be shaped by the environmental conditions of their home planets. For instance, if an alien species evolved in a high-gravity environment, their physical form would likely be adapted to that condition, resulting in forms that might be drastically different from human expectations. Contact with an extraterrestrial civilization could profoundly affect our society. Such an encounter might challenge our current beliefs and worldview, prompting us to re-evaluate our place in the universe. This could lead to a reassessment of our religious and philosophical beliefs, as well as our understanding of the origins of life. Additionally, it could raise ethical questions about how intelligent species should interact with one another and the responsibilities that come with such interactions. Another potential impact of encountering extraterrestrial life is on our technological and scientific development. If we were to come into contact with a more advanced civilization, we could learn from their technology and knowledge, accelerating our own progress. Conversely, if extraterrestrials were hostile, they could pose a significant threat. The challenge lies in determining whether extraterrestrials would be a danger to us, given our current lack of concrete evidence regarding their existence and intentions. Some people argue that if aliens are technologically advanced enough to conquer or destroy us, they might be highly dangerous. Others suggest that any civilization capable of interstellar travel might possess a more nuanced understanding of the universe and might be more inclined towards peaceful and cooperative behaviour. It is also possible that extraterrestrials might be indifferent to us, simply observing us from afar without any intention of interaction. The intentions or behaviour of extraterrestrials remain uncertain, making it difficult to draw any definitive conclusions. Nevertheless, many scientists believe that the search for extraterrestrial life should be approached with an open mind and genuine curiosity, rather than fear or skepticism. Regardless of the potential impact of discovering intelligent life, our quest for knowledge and discovery continues. We will persist in developing new technologies and refining our methods for detecting signals and evidence of other civilizations. Even if the likelihood of finding intelligent life is slim, the pursuit of knowledge and understanding remains a valuable endeavour. Several hypotheses based on the Fermi paradox suggest that advanced extraterrestrial civilizations may have existed for a significant period, but have been extinguished by certain natural filters. If these extraterrestrial civilizations do exist, their forms and environments might be vastly different from those on Earth. This idea arises from the theory that certain filtering conditions, whether astrophysical, physical, biological, or social, act as constraints on the emergence and development of advanced civilizations. Potential filters might include catastrophic events, astrophysical phenomena, or self-destructive behaviours inherent to intelligent societies. If extraterrestrial life does indeed exist, their forms and environments might not resemble those on Earth. Life could evolve in diverse ways depending on the unique conditions of each planet. The variety of planetary environments and the adaptability of life mean that alien organisms might possess different biochemistries and physical characteristics. Earth-like rocky planets are often considered ideal for supporting life due to their specific conditions. But these planets are also quite vulnerable to various threats. One significant threat comes from intense stellar events such as gamma-ray bursts. These bursts are incredibly powerful and can obliterate planets in distant parts of the universe, potentially affecting entire galaxies. Imagine a massive star exploding in our galaxy, releasing a devastating energy shockwave directed at our planet. Gamma ray bursts are among the most energetic explosions since the Big Bang, occurring without warning and emitting radiation that could heat the upper atmosphere, causing our ozone layer and even the entire atmosphere to warm. The result would be catastrophic for life on Earth. Humans would face lethal radiation exposure, and the destruction of the ozone layer would lead to deadly levels of radiation reaching the surface. Increased temperatures would trigger violent storms, tsunamis, and hurricanes, wreaking havoc on both land and sea. Most life forms would face extinction. Although this scenario might sound like science fiction, if a gamma-ray burst were to strike Earth, it would be a catastrophic event. Even if some intelligent species managed to survive such natural disasters, the impact would still be devastating. Additionally, another risk is self-destruction. This risk is derived from our experiences on Earth, where technological advancements have given us the power to alter the climate and develop destructive weapons. The brief lifespan of advanced civilizations could be one reason why there are so few observable civilizations. Many civilizations might have arisen, but their existence was short-lived due to self-inflicted destruction. The rarity of enduring civilizations could explain the limited opportunities for interaction with extraterrestrial beings. If we were to discover a civilization that has self-destructed due to pollution or conflict, it would highlight the importance of avoiding similar pitfalls in our own quest to understand the universe. We can only hope that some advanced alien species have successfully navigated these cosmic filters. If we are fortunate, we might witness a civilization that has managed to thrive and endure over long periods. Looking ahead, it is possible that an extraterrestrial civilization might visit us. Although we often assume that aliens would be similar to us, the reality might be quite different. Our understanding of life on Earth shapes our expectations, leading us to imagine that aliens live on planets akin to ours. However, most life in the universe might not follow the same rules or conditions that we are familiar with. The search for extraterrestrial life and the Fermi paradox raise profound questions about our place in the cosmos and the nature of life beyond Earth. As we continue to explore and seek answers, we must remain open to the possibility that the universe holds many more mysteries than we currently comprehend. In July of a notable year, a satellite dedicated to executing various test missions made a groundbreaking discovery. A new exoplanet designated GEG 357. This celestial body is situated approximately 31 light-years away from Earth and boasts a mass exceeding 6 times that of our planet. Such a planet falls into the category of super-Earth, a term used to describe exoplanets with masses larger than Earth's, but not large enough to be classified as gas giants. The term super-Earth implies that these planets, while larger, are still composed of solid material rather than gas. The substantial mass of GG 357 suggests that it possesses a significantly stronger gravitational force compared to Earth. This enhanced gravitational pull on a super-Earth could fundamentally alter the environmental conditions found there. Imagine the kind of life that could evolve on such a planet, where gravity is so intense that life forms might be adapted to cope with the heavier gravitational forces. On a super-Earth, organisms might evolve to be smaller in stature, but more robust and resilient. Such a planet represents just one example among countless others in the universe, each potentially harbouring unique and unexpected features. The universe, in its vastness, can be thought of as a colossal playground, filled with a staggering array of planets and stars, each contributing to a cosmic mosaic of diverse and dynamic environments. The cosmos is teeming with planets of all shapes and sizes, orbiting around stars that vary widely in type and size. This incredible diversity creates a multitude of potential habitats for life, far beyond what we can currently conceive. It is crucial for us to challenge our preconceived notions about extraterrestrial life forms. If we confine our expectations to beings with physical characteristics similar to humans, such as having 2 legs, 2 arms, and other familiar traits, we may be setting ourselves up for disappointment. Life beyond Earth could be fundamentally different, shaped by entirely different conditions and evolutionary pressures. Consider the intriguing scenario of an intelligent alien species from a neighbouring star system attempting to initiate contact with humanity. If these extraterrestrials evolved under the unique conditions of a super-Earth or orbited a star that differs significantly from our Sun, such as a red dwarf star, their biological characteristics might be so alien that we would struggle to recognise them or communicate effectively. Their adaptations to their specific environment could make them almost unrecognisable to us. On Earth, life appears perfectly suited to our planet's particular conditions, including its temperature, elemental composition, and overall environment. If an exoplanet possesses conditions that support life forms drastically different from those found on Earth, this could profoundly challenge and expand our understanding of what constitutes a viable living environment. The discovery of new exoplanets and their varying environmental conditions can offer insights into how life might develop in different settings. Even minor differences in environmental factors can lead to the creation of entirely unique ecosystems. Thus, the fundamental question arises: if extraterrestrial life were to visit Earth, could it genuinely adapt to our ecosystem? Our oceans, for instance, play a critical role in sustaining life on our planet. For a long time, it was believed that Earth's oceans were uniquely suited to supporting life. However, recent discoveries have revealed that oceans are not exclusive to Earth. Similar oceanic systems have been found in various locations within our solar system, indicating that the search for extraterrestrial life could extend to these new and unfamiliar environments. Water is a crucial element for life as we understand it, and it has been a primary focus of scientists searching for extraterrestrial life. The necessity of water for all known life forms on Earth has led to the formulation of a simple criterion for identifying potential habitats for extraterrestrial life. Look for liquid water. Initially, it seemed that Earth was the only planet within our solar system with the right conditions for liquid water. The concept of a habitable zone suggests that a planet needs to be within a specific distance from its star to allow water to exist in liquid form on its surface. For instance, Venus is too close to the Sun and is extremely hot, while Mars is considered too distant. The exploration of Mars has been a central topic for scientists and space enthusiasts. Despite its barren and desolate appearance, Mars has captivated interest due to the possibility that it may once have harboured liquid water. Recent missions have intensified the search for evidence of liquid water, or its historical presence on Mars. This pursuit is driven not only by scientific curiosity, but also by the potential to uncover clues about Mars' past and present, and perhaps even reveal signs of extraterrestrial life. Although extensive knowledge about Mars has been accumulated over decades of exploration, current evidence indicates that the planet is dry and cold, seemingly devoid of life. The question remains whether Mars has always been this arid. Scientists are now investigating ancient Martian oceans by studying one of the driest places on Earth, the Atacama Desert in Chile. The connection between Mars and the Atacama Desert lies in their extreme dryness. Mars is known for its aridity, while the Atacama Desert is one of the driest places on Earth. Interestingly, the relative humidity measurements taken by the Curiosity rover on Mars are almost identical to those recorded in the Atacama Desert. The Atacama Desert's dryness makes it an ideal location for constructing some of the world's largest telescopes. The absence of atmospheric water is advantageous for astronomical observations, as water vapour can interfere with the detection of celestial phenomena. Scientists are specifically searching for water and organic materials on Mars, and observations through telescopes have provided valuable insights into the planet's surface features. Current findings indicate that Mars has ice at its poles, and its surface suggests that liquid water may have been present in the past. This raises questions about the historical volume of water on Mars. In 1984, a significant discovery was made in Antarctica, another desert on Earth, where scientists found a Martian meteorite. The analysis of this meteorite provided crucial information about Mars's water history. This meteorite, estimated to be about 4.5 billion years old, contains important chemical data and isotopic signatures that reflect the amount of water on Mars billions of years ago. Although this feature might seem minor, comparing isotopic measurements from ancient meteorites with current Martian samples has revealed that Mars once had nearly 7 times more water than it does now. Observations of Mars topography show a planet with northern lowlands and southern highlands. If water flowed across the surface, it would naturally move towards the northern plains. The exploration of Mars reveals an ancient narrative. Around 4.5 billion years ago, Mars had vast oceans that could rival the Mediterranean Sea in depth. Models of Mars' past depict a planet with a warm climate and an atmosphere similar to Earth's. If one were to travel back in time to early Mars, they would likely land in an ancient ocean. With its lower gravity, Mars could have had ocean waves twice as high as those on Earth. Early Martian water and a thicker atmosphere made the planet warmer and more hospitable, despite its greater distance from the Sun. This period marked the most habitable time in Mars history, comparable to Earth's formative stages. Interestingly, despite the promising conditions, life on Earth began around this time, while Mars' early oceans faced a tragic fate. Over 1.5 billion years, Mars' atmosphere deteriorated due to solar radiation, eventually evaporating and leaving only traces of ice at the poles. The lingering question is whether ancient Martian oceans harboured life. If life did exist, could anything have survived to the present day? The Curiosity rover is on a mission to determine whether liquid water might still be present on Mars. Since its arrival on Mars in 2012, this mission has become a crucial component of planetary exploration. The stunning images captured by the rover, such as the blue sunsets, challenge our perceptions of the red planet. Photographs of Martian craters, such as Newton crater, provide further insights into the planet's water history. The geological formations and patterns observed on Mars suggest that water might have existed in the past. Despite the challenges of studying distant exoplanets, the discovery of new worlds continues to expand our understanding of the cosmos. Each exoplanet is unique, with its own set of characteristics that set it apart from others. NASA's Kepler Space Telescope, launched in 2009, has been instrumental in identifying new planets orbiting other stars. Over the course of its 6-year mission, Kepler has discovered over 400 exoplanets, including both massive gas giants and rocky worlds. This extensive catalogue of exoplanets demonstrates the incredible diversity of planetary systems beyond our solar system. The Milky Way galaxy, which contains approximately 200 billion stars, is thought to host billions of planets. The discovery of exoplanets has revealed a broad range of planetary types and orbital patterns, highlighting the diversity of planetary systems in our galaxy. For instance, some exoplanets are massive gas giants several times the size of Jupiter, while others are rocky worlds significantly larger than Earth. Additionally, some exoplanets follow highly eccentric or unstable orbits. The variety among these new worlds underscores the uniqueness of each planet. While studying these distant exoplanets presents challenges, our understanding of planetary systems has been greatly enhanced by the exploration of our own solar system. Our solar system consists of 2 main types of planets: rocky planets, Mercury, Venus, Earth and Mars, and gas giants, Jupiter, Saturn, Uranus and Neptune. Each of these 8 planets developed its own unique characteristics over the past 4.6 billion years. As the Sun ignited, it released vast clouds of gas and dust from which the planets formed. Despite their different compositions and locations within the solar system, all 8 planets originated from the same primordial material. In summary, the exploration of exoplanets and our continued study of Mars and other celestial bodies reveal the incredible diversity of the universe. The discovery of new worlds, each with its own unique characteristics, expands our understanding of what is possible in the cosmos. As we continue to explore and discover, we are likely to encounter even more surprising and diverse planets, each adding to the rich tapestry of the universe.